Let's redo this example we did last time using the method of distribution functions, but this time using the method of substitution. So you've got a continuous random variable x, you know its PDF, you have a new continuous random variable y defined in terms of x, and I want to find its PDF. The method of distribution functions, it can take a while because we had to find the distribution function, the CDF for x, which takes a while. Now there's this method, the method of substitution, you go straight from the PDF of x to the PDF of y. It's going to be quicker. Let's see how it works. What we're going to do is we're going to take the PDF for x, and we're going to add a dx. Just like, imagine it's in an integral. So imagine you've got something like this. You have a little dx, like you would in an integral. So we've got this thing, 1 over 1 plus x dx. 1 over 1 plus x dx. And what we're going to do is we're going to do the same thing we do in integration by substitution. We're going to make this substitution. So imagine you have a new variable y and your old variable x, and you substitute y equals 1/2 root 1 plus x. But you really substitute just like real number variables, little y and little x, just like you would when you do integration by substitution. So you have a real number variable, little y, and I'm going to substitute, what was it? 1/2 root 1 plus x. 1/2 root 1 plus little x. And now the idea is what I'm going to try and do is do the mechanics of the substitution just like I would in integration by substitution and rewrite everything in terms of little y and d little y. And what should come out is the PDF of y. So here we go. If this is y, well, we're going to have to figure out what dy is. I'm going to take the derivative here, 1/2 1 over 2 root stuff times the derivative of the stuff, just 1 in this case. I'm doing the chain rule. All right, and then let's maybe simplify this a little bit. We're going to try and, oh, whoops, I forgot. It's going to be that dx, right? Of course. Okay, and now let's simplify this a bit. dy equals 1 over 4 root 1 plus little x, d little x. And I want to isolate dx here, so we're going to get d little x is, multiply this up, 4 times root 1 plus little x, dy. Right? That looks good to me. Okay, I'll leave some more room here. So, let's see what we got. 1 over 1 plus little x. Now my dx turns into a 4 times square root 1 plus little x dy. Okay. So now I've got a dy, but I've got these x's, and I want them to be y's. So I'm going to have to use this relationship between x and y to try and rewrite these guys in terms of only y's. So let's simplify this a bit first. We've got a square root on the bottom and this guy, sorry, on the top and this guy on the bottom. 4 is going to be on the top. I have this guy right here, it looks like. And okay, so root 1 plus x down here, and I have y equals 1/2 root 1 plus x. So if I multiply both sides by 2, right, if I were to do that, I would get 2y equals root 1 plus little x, right? So I can replace this guy with a 2y. 4 over 2y dy, and that just comes out to be 2 over y. And that's the same thing we got when we did the method of distribution functions. But that was quite a bit faster. Okay, and the one thing that remains to be done is to say, well, our PDF for x was this function on a certain interval. It was 0 everywhere else. So I have to look back here and I go, okay, it was this function on this interval. So our PDF for y is going to be this function on what interval? Well, the corresponding interval for y. So I take this interval, all the numbers in this interval, and I run them through this function, thinking of y as a function of x. Imagine plugging all these values of x in here. What interval do you get for y? And again, we can just plug the smallest and the biggest because it turns out this is an increasing function. So this method, it only works if this function that defines y in terms of x is 1 to 1, meaning it's either increasing or decreasing. So you should check this is an increasing function. This graph is always going up and right. It never turns over and goes down. Cool. And you can check that. You've done calculus. Take the derivative. You can check it's always positive. If you like, you can just plug it in Desmos or something like that and just see a picture of the graph and check. But yeah, it turns out this thing is an increasing function. So if I plug in 0, I'll get the smallest value. I plug in e minus 1, I'll get the biggest value. We did that in the last example, so why redo it? What did we do? We plugged them in and we got these two things, right? 1/2 and 1/2 root e. Same deal here. So, great. So this thing, the thing that comes out, is fy of little y. Just to make that very clear, it's not a capital Y. Fy of little y d little y. Cool. So method of substitution. You start with the PDF of x dx. You make a substitution y in terms of x, where this function, this substitution right here, is really the definition of y in terms of x. But you're just doing it as if you're doing integration by substitution with real number variables. Make the substitution, rewrite everything in terms of the new variable, little y, and what you'll get is the PDF for y with a dy after it. Okay, great. So let's just finish up by writing it out. So fy of little y is equal to 2 over y on the interval. We just went through this, right? What was it? Yeah, we did this before. 1/2 root e, which I got by plugging 0 in here and e minus 1 in here. 1/2 root e. Perfect.